Alright, hello and welcome to the next lecture in the trees set of slides. So what we're going to do is finish these up, and we stopped down here where I was talking about the different kinds of traversals for trees, gave the algorithms, gave some examples, gave you racket code, and now it's your turn to try and remember all of these terms. So I want you to take this tree, A, B, C, D, E, F, and G, just like that, and do a post-order, pre-order, in-order, and breadth-first traversal of them. And by traversal, I just mean when you process the node, just say what it was. So give me the order in which you visit and do the processing of each node. Okay, so give that a try, write it all out, and then we'll do it together. Okay, so first is post-order. And remember that pre and post and in kind of are telling you in what order do I visit the root. Okay, that's what those really mean. So post order is going to process the root, the current node that you're looking at, the root of your subtree, after the children have been processed. Okay, and pre does it before. So if we just remember in the back of our minds left-right root for post order, that is going to end well for us. Okay, so we start at the root always, and we're going to go left, right, root, always. And when I say left and right, I mean recursively visit left and right. So left, right, root, starting at A. Okay, we're going left. Let's work on this guy. Okay, left, right, root again. Now we're down here. Left, right, root, left, right, there's nothing, D. So D's the very first thing that happens. You see that? And so that was the root. And then again, we did the left, do the right, there's nothing, and then root, so B. Okay? And then we did all the left. Now we need to do all the right of this subtree. Subtree rooted at C now needs to happen. And you go left, right, root. Okay? Left recursively, so let's process this entire subtree recursively. Left, right, root, so left, right, root again. Nothing, and G. Okay? See how this is working? I encourage you to draw the stack, like how it's calling these things, if this is still confusing. So left, right, root, left, right, then root again, so E. And then we did all the left, we need to do all the right here, which is going to amount to being F, and then root, which is C, and then we did finally left, right, time for the root, A, okay? So I don't know an easier way to demonstrate all that than just writing all over this, but hopefully that made sense. Okay, so that'll be the post-order traversal, always left, right, root. And now we do pre-order, which is root, left, right, okay? Always visit the root first, then recursively visit the left and right children. Those left and right subtrees, that is. Okay, so starting with pre-order, let's start from the root. So it's root, left, right. So we got A, left, right. So let's do the pre-order traversal of the subtree rooted at B. All right, so root, left, right, we got our B. Left, right, okay. This one's a leaf. I think you understand that it's going to be root, which is D, and then left, right, we're done with you. And then we come back to B, and we did the left, we need to do the right, there's nothing there, we're good, and then we're done with the entire left subtree. Okay, so now we did the root, we did the left, we now need to do the right of the outermost subtree, of A's right child. We do its right, okay? So let's recursively do the pre-order of the subtree rooted at C, and so we do root, that's the C, and then left, right. Okay, let's recursively traverse the subtree rooted at E now. Root, E, then left, G, right, nothing. Done with that. We did root, left, right. Now we have F. And that completes the root, left, right of the outermost tree. Okay? The original tree that we were given. Okay? Very, very nice. Now in order, that one is left, right, root. Ready? So first we do the left of the whole thing. Or sorry, we do left, root, right. Okay, root's in the middle. Do left, root, right, and so now we're doing left. Okay, so we do left, root, right, which is going to be D is left, B is root, right is nothing. Okay, we're good then. We did the left, we now do the root, A. Then we do the right here. Okay, and we do the whole thing all over again. Okay, so we do left, root, right. So let's do left, okay, which again is going to be a left, root, right, so GE, and nothing for the right. Left, root, C, right, F. Okay, so do double check me with the programs that I wrote in Racket. That would be a very good exercise. but I'm pretty sure that is the way it should be. And then breadth first is the easiest. It's just level order. Okay. So breadth first traversal is going to do always A, B, C, D, E, F, G in this case. Okay, which is quite nice as a last one. It's a relief, right? So that is all of those traversals. I want you to pretend to be the computer. I want you to have the little stack in your mind of where you're going and where you need to come back to. Okay. Please yell at me if you have any questions at all about how to do that, and I can just give you a ton of examples until it makes sense. Okay, so now here's something that I want you to do. It's recursive algorithms on trees themselves, okay? Because I've shown you like some of them, like post order, pre-order, and in order, and you can more or less take those as a starting point to do whatever you want. If you want to find some information out about a tree, it's really not too bad to adapt like a post order to do something. So let me show you, or I want you to give it a try first of all, and then I'll show you my my ideas for how to adapt the code above to compute the shortest distance from the root to a leaf. Okay, so if here's my tree, I got boop, 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 and then maybe boop, boop, boop. The shortest leaf, shortest distance to a leaf is right there. It's 1, 2, right? Because here's the root. If we did that, that's what we want at least. So we want to figure out that, okay, we only have to go down 2 to get to the shortest thing. And this is going to end up being a recursive algorithm because we have subtrees where we can solve this smaller problem on, okay? And so that's what the recursive call is going to do. It'll solve this problem on a smaller subtree, okay? So here's my thoughts. You're essentially going to change like how process works. You're going to save the result of the recursive call. So let's call it something else. Let's be like, I don't know, what should we call this? Min dist or something. Closest leaf or something. Who knows? And you give it a initial vertex. You give it a v. Okay. And what it's going to do is, well, recursively, you're going to make calls to your children and figure out, well, which one has the shortest distance for that one. Because I think you can tell if we take both of these subtrees, if we just find the minimum distance of that, right? Here's the minimum distance subtree. It'll have the minimum distance to a leaf as 1, and we can assume that the recursion gives that back to us. So we get 1 back. It's just our job to add 2 now because we took away an edge, right? That's all we have to do. That's all we have to do is visit the subtrees and like figure out what's going on here. And let me, so that I can reuse this perhaps, make this one big line. That's the left subtree, that's the right subtree. Okay? And so we'll just recall on every child, again, min dist, like, and save the smallest one. Take the min dist, right? For each child of v, let's call it w, I guess, again, w of v, call min dist of w, so it's like the subtree rooted at this node and subtree rooted at this node, and save the min result. Because we get to assume that this is going to return back the minimum distance for the left subtree, the minimum distance for the right subtree, as long as we build up the final answer correctly. It's just recursion. So then we can return that min plus 1. Okay, so that's the recursive case. The base case is if we have an empty tree. Okay, what is the distance from nowhere to, like if we're right here, like what's the distance from nowhere to the root is, I guess, the question. And so you could stop either at a leaf. You could be like, okay, if I'm ever called with a leaf, the min distance is should be 0, right? Which means if you're ever called with a, let's see here, if you're ever called, yeah, if you're ever called with an empty tree, you can give back -1 if you wanted to. But how about we just do leaves, okay? Let's just assume that we always have something in the tree. if v is a leaf, return -1. And I have not really given myself enough room for that, but I hope you can see it. If we are a leaf, if v is a leaf, return -1, or sorry, 0. Let's do it this way. Leaf and not empty tree. If it's a leaf, return 0. And so here's what's going to happen. We're going to recurse left right. This is going to be the useful one. It's a leaf. We'll get back 0 from that call, add 1, give back, so this gives back 0. This recursive call will give back 1, and then this final call, this original call, will give back 2. See that? Because it'll always find the min. Like this side will give back 2, that's not good enough. This side will give back 3, that's not good enough. And so that is the hope, that all of these things will give back first 0, then 1, then finally 2. Okay? It'll find the minimum thing. Okay? So that's, again, don't let it fool you. This is post order. Look at it. Mindist, mindist. We're making recursive calls first, and then processing our current node, which involves, okay, worrying about the children's answer, and using that to make our own final answer. Okay? So that is my sketchy little min-dist algorithm, and I hope you can see how it's very similar to post order. Okay, and yeah, that's I guess the standard way of doing that. Okay, so that is a nice way of modifying a recursive tree algorithm to do what we want. And remember, it's because it's recursive, we get to assume that the smaller calls on the smaller subtrees are going to give us back the right answer. Okay, so that is that for recursive calls and things. I now want to talk about spanning trees, which kind of links together graphs and trees once more. So a spanning tree of a graph, and the graph has to be connected, it's a subgraph, which means you pick out some vertices, you pick out some edges. This particular subgraph that we're calling a spanning tree, it must contain all the vertices, so it's got to keep them all, and it's also going to be a tree. Okay, so it's one way of making a tree out of a graph. Okay, a spanning tree is a way of making a tree out of a connected graph. That's all. So here is the same graph a bunch of times. Just consider that every edge is either red or black, and here are 3 different ways to make spanning trees out of this graph. Okay, so notice that there's no cycles. If I added one more, I would have a cycle now. Okay, so these are all spanning trees. There are no cycles. It's connected too. Okay, so these are 3 different ways of creating spanning trees for this graph. I can't remember if this is all the ways, but it very well could be. And yeah, it's a very common thing to want to do to make a spanning tree out of a graph. Like, what's the minimum amount of routers I need on my network, for example, so that I can get a packet A from my router to my to Comcast's router or something. Okay, so that is a spanning tree, and believe it or not, we already know how to create those. Okay, so remember the graph traversals from the graphs slides? We actually made spanning trees out of graphs with those traversals. So all of our graph traversals, breadth first search, depth first search, those all discovered, the entire graph. They looked at every node, they visited every vertex, right? And one key thing of our graph traversals that we know and love is that they never revisited a vertex, right? They never revisited a vertex, which means that they are making a spanning tree. Okay, we visited everybody, so we were connected. We followed enough edges to get connected, and we visited all the nodes, so we are a tree as well. Okay, isn't that quite nice? So let me show you DFS and BFS again, just to jog your memory, and that'll be that. So graph traversals, depth first search, remember it used a stack, right? We pushed our starting vertex, and then we just made a tree out of this graph. We really did make a tree, okay? And yeah, we just picked off a vertex at a time, added it to our visited set, and if we wanted to save the edges, this would have made the tree. Okay, BFS is similar, just we replaced a queue with a stack, or sorry, a stack with a queue. That is all. And again, it visits all the nodes in a certain order, visiting certain edges along the way, and that creates a tree, in fact. So it's like, okay, I went from A to B like this, so that's part of my tree. It's part of my spanning tree that I'm discovering. Okay, That's quite nice. So yeah, one last thing I want to say that I kind of got into in the slides up above here is that DFS, depth first search for graphs even, can be recursive. It's kind of like a post order for graphs, okay? So it's possible to, instead of a stack, just let the recursion happen and use the function call stack as your stack, okay? So let me show you how that's working. It's all the same time complexity, same everything, same runtime and space complexity, because you're still using a stack at the end of the day. Instead of an explicit one, you're using an implicit one. Okay, so let me show you this one. All this stuff, DFS. Are you ready? And one thing that you have to do differently though, because this is now recursive, is you got to plop visited outside. It's got to be global, okay? Because otherwise you're going to keep calling DFS. You can't keep making your visited set empty every time you make a recursive call. Yeah, so that's this moved. Okay, maybe I should say global var now, something like that. Yeah, but it's a little bit off the edge, darn. Okay, I'm happy. All right, so that is DFS, and let me just go through this. Okay, not too bad. We're gonna remember it. Same graph. We're gonna start at A again. Are you ready? So our visited set starts out empty, and I will just do myself a favor and not draw a closing thing. And the function call stack, instead of writing it like this, from bottom to top, I'm going to write it from left to right. So here is like leftmost, this is like the middle, this is the right, this would look like this in my drawing, LMR. Okay, the top is going to be over here. Okay, that's how I'm going to draw it. So the very first thing we do is we say DFS G at a certain edge. So we say DFS at, for example, A. So I'm going to say that we called it at A. That's how I'm going to write it. Okay. So then we say, okay, let's plop into the first call to DFS at A on G. This is graph G over here. Okay. So, and oops, I am sorry. I forgot to take out the while loop. There is no stack anymore, so it's going to be implicit. It's all fine. Okay. So this is what it's going to look like. So we start with A, calling it at A, and we want to visit everybody. Okay. So if my current node that I'm looking at, if my current vertex V, which is A right now, if it's not visited, well, let's visit it. Let's process the node, and so we're going to say, yes, we have visited it now on this line. And then for every adjacent vertex, we are going to DFS it. See that? That's where our implicit stack happens. We're making a recursive call here. Okay, so let's just do it in alphabetical order. B, C, and E, we are going to call on our stack first. So first goes the B. So now we're going to DFS starting G at B. See that? Oh no. So now we're starting at B, and my mouse does not want to cooperate. So now we're up here with V equal to B. We have not yet visited it, so what we will do is we will visit it, okay? And yeah, I'm sorry, my mouse is just really not happy. It thinks that I'm clicking when I'm not. Maybe I can just use the arrows. There we go. So now we're here, and we're going to process B, okay? Ready? So we're going to visit it, because now we're like that, and then we're going to recursively visit all of B's adjacent vertices, which are going to include A, D, and F. So let's do it in order. We're going to do A, D, and F. So first comes A, and I think you can imagine that we're already visited in A, so we're not going to continue this. We return, and now we're trying to do the next adjacent vertex to B, which is going to be D. See that? And so, yeah, this is how it's going to work. So we do D here, and then after that, we visit all of D's adjacent vertices, and so we're going to add B, for example, but B's already been visited, so we'll pop it right back off, and yeah, that's the name of the game. Another thing that you could do, like we were talking about last time, is you can just say unvisited. So push all the unvisited adjacent vertices, where W is unvisited. Let's just do that. That makes it easier on us. And so now we don't have to consider B, so we're done processing D. Okay, D's gone. And so now we're doing more of B's. We're still working on B's unvisited adjacent vertices, so we still have F to worry about. So we're going to push F, which means call DFS G comma F. Yeah, that's the idea. And so now we visited F, and sorry, I should remember the order. I guess it's 1, 2, 3, 4, and then we do F's adjacent vertices, which is dun dun dun. B has already been visited, but E has not. So let's add E to this recursive call. And so we're going to make the recursive call and visit E now. Visit E, add it to the visited set in that order. So now we have 5, and then we can say, okay, what's E's adjacent vertices? E and A, or sorry, F and A, but we've already visited those, so we won't push them. So we're done visiting E. And then we're back to F, but we visited all of its children, so now I can pop that off the function call stack. And then we're done visiting all of B's children, right? Yes, we are. And so we can pop that off the stack, and now we need to finish, because we were waiting in another recursive call. We were working on A's children, right? All of its adjacent vertices. So now we have C. Okay, that's the next one. So let's push C to the stack, which means call DFS G comma C. And so we'll visit C, walk through all this stuff, add, and then make a recursive call for all of its unvisited things. So not A, we visited A already. So let's visit G now. Okay, oops. And so C was the 6th thing, and G is the next thing that we visit, which will be the 7th thing. Add G to our visited set, and now, finally, we can pop everybody off, because G's adjacent vertices have all been visited, same with C's, same with A's. Okay, so our stack is empty, our visited set looks like this, and this is the order in which we visited everybody. Okay, and I think, if I did it right, it's all essentially the same. Let's see, A, B, D. It might be a bit different, and I'm not yet sure why. Let me pause the video, make sure I didn't make any mistakes. Okay, yeah, I'm happy, because I think what I did last time is I pushed these vertices in order, which means that I visited them in reverse order. So like E was the first thing that we visited. Yeah, that was the problem. So that means that we visited these in a weird order. You can push them in reverse if you'd like, and it would be the same. So that should be fine. But what happened was, look what we did. Every time we crossed a path, every time we added a new thing, every time we made a recursive call to a child, we essentially added an edge in our spanning tree. See that? 2, 3, 2 to 4. We got there from B, and then we got here from F. We got from F to E. And then from A, we got to C and to G, and this makes a spanning tree. See, we didn't consider this edge because that would have made a cycle. We don't like cycles in trees, and that made a spanning tree for us. Isn't that nice? So that is the recursive version of depth first search, and now I'm finally spelling out to you why it's making a spanning tree. Okay, so that's what it's doing, and yeah, let's continue. So what I'd like you to do now is I want you to do BFS and DFS, and like add all the neighbors, consider all the neighbors in an alphabetical order. So if you're using the real stack version of depth first search, I think that means add them in reverse order, but either way it's going to work, don't worry. So even if we get a different answer, it's still a very good exercise. So yeah, let us do this together after you give it a try yourself. All right, so the very first thing that I guess I want to do is probably make another copy of this so that I can do BFS over here and DFS over there. So BFS, which one do we start at? We start at A. BFS adds everybody, considers everybody in queue form. So A is going to add to its queue of things to visit first B, right? So it'll visit B from A because we haven't visited it yet. It'll visit then E from A because we haven't visited it yet. Then f from A, because we still haven't visited that yet, right? So it'll always do its children in order without considering their children yet. Yeah? That is the whole point. And then we will have added all of their children, which is like, okay, B, but we don't need it anymore, F, but we don't need it anymore, things like that. Then we come to F, and then F considers all of its children in alphabetical order, adding them to a queue. Okay, so I want you to have the queue in the back of your mind. Maybe write it out like I did in the graph slides. That will help you like make sense of all this. So first F adds both of its children, so it's like, okay, we're going to C from F and to D from F, and that actually makes the spanning tree because no other edges are needed because we've already added them. Okay, we've already added those vertices across those edges. So this looks like a bit of a fish, and that is our BFS spanning tree. And DFS is going to be a bit different because it tries to go as far away from the root as possible. Okay, so here's what's going to happen. So first, A is going to recursively visit all of its children as much as it can. So, and then backtrack if it ever like can't go any farther. Okay, so A is going to first look at B. It's going to traverse looking at B. Okay, it's like, okay, let's call DFS at B, see what's there. And then it'll go in order. Okay, I've already visited A, let's visit E, that's the next thing in alphabetical order. Okay, let's from E visit everything. Okay, we've already visited A, so backtrack. This is what the stack is going to do. It's going to unwind, and then we're back at B. That was the most recent place we were, where we had an option. So then we're going to go to F from B. See that? That's exactly what's going to happen. We're not back at A yet because of the stack. The first call was at A, then it was at B, then it was at E, and then we're popping off the stack. See that? Now we're at F. Now we're at F up here. That's the idea. And so F is going to recursively visit all of its unvisited children. So A is out of the question because we've already visited it. But then we'll go to C. All right, so it's going to visit C from F. And then D from C, because it's always going to keep making recursive calls. So this is what it looks like, and it's kind of like almost backwards, but a bit different. So it's making really long paths, if it can, through this graph. It's trying to get to the very bottom. It's trying to get to a faraway leaf, I guess, in this tree. So that's why these look the way they do. A kind of stays, or BFS tree kind of stays close to home, and DFS like wants to run away. Okay, so I do encourage you to like spell it out, write these sets, and just do it in order. If what I just explained didn't make enough sense, okay? I promise it is a good thing to know. Okay, now let's add weights, and this is the last thing. So a minimum spanning tree is when you have a weighted graph. Okay, it's not just a bunch of vertices and edges, it's vertices, edges, and weights, 8, 7, 6, all those things. Okay, that is a wonderful thing because sometimes we have trees that look like this, or sorry, graphs that look like this, and we want to make a tree like maybe pave some roads or something so we can get from place A to place B with the cheapest cost. Like maybe we gotta like build a bridge for this one. We don't want to do that if we don't have to, right? That's the idea. So we want to make the minimum spanning tree. That gives us the spanning tree whose edges, if you sum the weights along all the edges of the spanning tree, those are the minimum. Okay, that's the idea. And one such algorithm that finds a minimum spanning tree, it may or may not be unique because there might be several different spanning trees with the same minimum weight. It's called Prim's algorithm. Okay, so let me show you this one. And let me first say its intuition. What it does is it realizes that, okay, every vertex, it needs to end up in the minimum spanning tree. So we can just start with whatever vertex we want. Let's just be like, okay, F's going here. So then let's look at all the ways we can expand this tree starting at F, for example. That's what the algorithm's going to do. Okay, and what it does is it adds a minimum edge each round from where it is, which guarantees that you can't find a better way, because like when it sees F, it's like, okay, the first thing that I'm going to add is H, because there's no better way for me to get to H. Okay, that is its thought process. There's no way I could be going somewhere else in a better way. Okay, that is the hope. So that is Prim's algorithm, and that is what I'm about to teach you. So what happens is all of this pseudocode over here. It's really not too bad. I'm going to show it to you. It does look quite a bit bad, quite a bit worse in Racket, but there's a lot of it's a lot of pushing symbols around when you program it. But in pseudocode, at least, it's really not too hard to understand. What you're doing is you're taking in a graph G, and you're outputting a tree T, which is the minimum spanning tree. And you can just assume that, okay, maybe you're representing the tree as like a set of the edges in the graph or something like that, whatever you want to think about it as. But you're going to build up the tree slowly, okay? And the first thing you do is pick your starting vertex and just be like, okay, this is the one. I'm adding it to my spanning tree. I need this eventually. Let's just start with a random vertex. And then what it does for n-1 tries, because it needs to make a tree which has exactly n-1 edges, what it does is it goes and it finds everybody on what's called a frontier. It goes and looks to see, okay, what are all the edges that I could add right now to this spanning tree to increase its size by 1, okay? With one endpoint inside my current tree and one endpoint outside my current tree, okay? Because it's going to try and add vertices one at a time. And as long as it keeps adding the minimum weight edge of all the ones that it gets to choose from, keep adding that, and then that is the one that you put in your spanning tree. That's all you have to do. It's a very simple algorithm. It's a bit harder to explain why it's computing the minimum spanning tree, but hopefully the intuition makes sense. Okay, so that is the idea, and let me show you an example of computing these minimum spanning trees now. Are you ready? So what we're going to do is we're going to start at A for this tree, or for this graph, excuse me, and compute the minimum spanning tree. So we're starting with A, and here is the graphical way of how I'm going to explain this. So we started here. We just picked our first vertex to start off our minimum spanning tree, and then we're going to consider our frontier and find the minimum weight edge to add to cross that frontier with one thing on our current tree and one thing not on our current tree. Okay, we're going to add the minimum weight edge, and that's going to give us the minimum spanning tree. So of all these ones that we could add, this one, this one, this one, or this one, which one are we going to pick? You guessed it, 0. This is definitely part of the minimum spanning tree, because the rest of these take time. Like if we went through this one, we'd be forced to go and take 8 or 17 to get to D. See that? We don't like that. So we're adding this one, and now it's part of our tree. So our tree has these 2 vertices and this one edge. See that? And then we're now going to consider all the possible ways we can get out of this. So now this is a candidate, this is a candidate, this is a candidate, this is a candidate. Which one do we pick? We pick the 8. See that? That's all we do. Bam. So now it's part of our minimum spanning tree. Okay, and now we have this one. So we can consider still this one, still this one, still this one. It's part of that, this one, or this one. Which one will we pick? And I think it's the 2, right? That's the minimum one, our minimum possibility. That's the 2. And so this is going to, if we play this game long enough, it's going to create our minimum spanning tree. And I think the next one that we want to add is, of course, this one. It's the 1, the minimum amount. Okay? And we're going to finally cover all of this, and then we will be happy, I think. Okay, with the minimum tree. So all of the options, we can go out this one, this one, this one. What's the minimum one we could use? The minimum edge we could add where 1 is inside, 1 is outside. It's this E. We go to 3. We follow the edge along F and E by 3. Okay, and so we just keep playing this game, find the next minimum thing on our frontier, which is all the edges we can go out of to get to somewhere that we haven't seen yet. Okay, that's the idea. So which of these are we going to do? Can't use this one yet. And I think we're going to do the 5 then. Okay, that one, and then we'll do the 4. Okay, so that is that. I think if we did it enough, there may be multiple different minimum spanning trees. I'm really not sure by looking at this if that's the case or not, but that is the idea. So we started here, we added this one, then we added this one, then we added the 3, the 5, the 2, the 1, the 3, the 5, the 4, and I think that gave us the minimum spanning tree. So look how, if we wanted to get to F, obviously we're not going to take 9, we're going to go through D by 8. See that? See how it's helping us out like that? So this is the minimum tree where the sum of the weights on all these edges make us our spanning tree. Okay, so that is Prim's algorithm in a nutshell. It's very graphical. It's very nice to wrap your head around. And so what I want you to do is try it for this one, where you can have negative weights. It's totally fine. It still works out just fine. So again, I want you to start at A and give this one a try. Make the minimum spanning tree, please. Okay? So, and then we'll do it together. So here's what's happening. It is, of course, going to first add the 0, because there aren't any negative edges yet. And so now we have A and E in our spanning tree. And now I see a negative edge. Is that the only one? Yeah, coming out of this and go that way, that way, that way, that way, that way. I think we'll add the negative 1, right? I apologize if I don't see the right one. Okay, negative 1 still. Yeah, we're going to add this one. What's better than a negative amount? If we want to go from A to I, it's only negative 2, right? And again, negative 2. Yeah, that's the next smallest one, right? And now we have to take a look. So 0.2 is a contender. Let's see here. Yeah, that looks like the smallest, right? Oh, sorry. No, 0.2 is not a contender because we've already visited G. Silly me, sorry. Let's see here. What are we going to do? Let's see. We could do 3. That's better than 4. Oh no, these are much better. 0.5 is the best I see so far versus 1, 2, and 3. Yeah, I think 0.5 is the winner here. Okay, so we're going to add 0.5, and that's how we get to B. Okay, and so now this one's out of the question because we already have a way to get to E. Yeah, that's the game. And so now we can't add this one. What are the ones we can consider? This one, this one, this one, this one, and this one. Which one's smallest? The 1, right? So here's how we're going to get to this one, and that suddenly frees open this negative 4.1, which is of course the one we're going to take next. And then the only other options are the ways we can get to this F right here. So 7, 11, or 3, we're going to take the 3. Okay? And I think, yeah, the only other one that we haven't visited yet, and the reason we haven't visited it was because of this high number. It's this G to H, and we're forced to take this only one right here. Okay? So that seems to be the minimum spanning tree, and that is the idea. Okay? Not too bad, I hope. That is Prim's algorithm in a nutshell. And what I want to show you, though, is how you can go from this code to a very, very inefficient implementation in Racket. Okay? This is more to like translate this to code rather than to make it fast. Okay? So let me show you it in Racket. I think if you tried it in C++, it would definitely be a lot faster because you could use some better data structures, and C++ is fancier and faster anyways, but this is still useful as you're learning. So here is my implementation of Prim's algorithm, and here's the graph, which took me a very, very long time to type up. Okay, I'm using the adjacency list representation, so I have a list of lists with lists inside. Okay, so the outer list contains a bunch of inner lists with the name of each node, and then we have an adjacency list inside here. Remember that brace, parenthesis, and square bracket, those all are the same in Racket, and I'm using those to like make it easier to look at. Okay, and so here's the adjacency list in between all of these curly braces. That's the word I'm looking for. So A can get to B, for example, with 0.5. A can get to C by 3. A can get to E with weight 0. Okay, so that's me doing all of this graph from this slide. And hopefully we'll see if it actually gives back the same minimum spanning tree. Okay, so here's Prim's algorithm. It's really not too different. So I'm going to keep track of my tree that I'm building up as a set that starts out empty. Mutable set just makes an empty set to begin with. So T's, vertices, and edges start out as the empty set, which is the empty set. Okay, so that's that. And then I'm going to get the length of g, which gives us the size of the graph. And yeah, I'm just going to add a random vertex, which happens to be the first one. That's the one I'm picking. I'm going to add the first vertex to my t, which is the tree that I'm building up. And then for n-1 times, because in range only goes, it doesn't include the last one, so it's from 1 to n-1 really. Well, here's the high-level idea. I made all these helper functions that you can look at if you'd like, but what it does is it finds all the edges across the boundary, which is the stuff that is part of our tree, stuff that's inside our tree and then outside our tree. Those are all the things that we should be considering, and we get the minimum one across that boundary, okay? Because it keeps track of all of the weights. And then once we've got the minimum one, we're going to add that to our tree that we're building up. So add it to our edge set, and I'll also keep track of the vertices. Okay, we'll also add that vertex, that new vertex to our set. And because I'm not sure which one it is, I'm just going to add both because this is a set. It doesn't have duplicates anyway. It doesn't matter. Okay, one of first / second min edge is already in t vertices, but it's easier to just add it again. It's not a big deal. And then, yeah, the answer is then finally the tree, which I'm just going to represent as the edges that make it up. Okay, so that is Prim's algorithm in a nutshell. The devil really is just in the details, like how do we find all the edges across this boundary? And so I have a bunch of helper functions. Like here's the helper function that has helper functions inside of it. It's like, okay, I need to get all the edges of G, which takes quite a bit of work. I encourage you to read that. We need to figure out if an edge is across our boundary. If part of it's in the vertex, like part of it's in one of our tree vertices, and one of it's not, like in, not in, yeah? Or the other way around. The end was in, but the start was out. That's the idea. And so really this is filtering all of our edges. Take all our edges and filter until we find all the ones that are across the boundary, and we want the min one, which means we take those edges that are across our boundary and sort it, yeah? And we take the first one. That'll be the min, yeah? So that's essentially the algorithm. What it does is it produces all these things, and here's what happens when you run it. I say prim g, and then I have some helper information that's printing out, like, okay, it's found this edge, it's going to add it, it's going to add it, it's going to add it, and hopefully it added the ones that we think. Okay, so we took the one from A to B with 0.5, and this is going to be the moment of truth to see if this is going to be what we got. Okay, A to B by 0.5, we took A to E by 0, yeah, that's not bad. We took D to E by 1, okay, D to E by 1, where's that one? Yes, sure. Then we took G to H by 4. We're kind of forced to take that one. Let's see if this is going to work out for us. We took F to J by 3. Okay, so that's part of it. And then we took C to D by negative 4.1. Definitely we want that one. And then we took G to I by negative 1. And we took the other negative 1 too, right? That was E to G, yeah, negative 1. And then I to J by negative 2. And mode of truth, if I flash over this quickly enough, is this the same one? Yeah. So the algorithm does work. It doesn't have any bugs, at least at this level. Okay, so that is the minimum spanning tree. I encourage you to read your book. It has a proof of why it's correct and why it works, but I think the intuition is enough for the slides, at least. It's going to build up this tree by considering all the edges that we could add to it and taking the minimum one. Surely that's going to do something right, yeah? So that's one of the cases where our intuition actually matches the right answer, which is a nice happy ending for once. And yeah, so please stare at this code. It's really helpful to learn another language by looking at other people's writing. And please yell at me if you have any questions about how any of this is arranged. I used some fancy Racket things, especially in these helper functions, but I would be happy to explain any of it to you, okay? Obviously, I'm not going to test you on anything from Racket, But I will, in your next lab, of course, be asking you to do tree stuff in C++. So this is a good refresher and a good way to get ready for that lab. Okay, so I think that's all I have for you in these slides. I will see you in your lab, and we will continue with that.